Hi, and welcome to section 7.3, which is the sampling distribution of a sample mean. Last section in 7.2, we focused on the sample proportion and the sampling distribution of a sample proportion. So for this section, since we're dealing with means, we're going to deal with quantitative variables. Because quantitative variables, things that we can measure, are things we're also able to calculate an average for. If we have quantitative data, we can use sample means my goodness, it's part of the board, to construct a sampling model. So, example, say I randomly select 100 seniors in Maryland and record each one's GPA. I'm interested in knowing the average GPA of a senior in Maryland. So, just for this example, let's say that I randomly selected from a pool 100 seniors, and I came up with all these GPAs listed down here. Then, out of all these 100 GPAs, I found the average, put them in my calculator, put them on L1, went to stat, over to calculator, 1-bar stat, and bam, I got the average. So these 100 seniors make up one possible sample of all the seniors in Maryland. The sample mean that we identify as X bar for these 100 seniors happen to be 2.547. Now I know some of you are thinking 2.5, that's not very good. Yeah, because your GPAs are higher than that, but these are seniors, non-possible STEM, non-IB, maybe they didn't all take AP. So that is their average for this one sample of 100. And the sample standard deviation, which we give a sigma, a little subnote X bar. Don't worry, you don't have to use that. You can just write it out. Happen to be 0.7150. So our parameter that we identify as mu is the true mean GPA of a senior in Maryland, which we could probably possibly know based on computer information or database. And our statistic, which we identify as X bar, is the mean GPA of a senior in Maryland in a simple random sample of size 100. This was just one sample, but as we did with the poker chips and the blue bucket, we took more than just one sample. So let's say that I took 10 different samples of size 100 and I computed all of their averages. So we picked 10 different samples, then the value of our statistic, X bar, changes with each sample that we draw. Next page. Okay. If I graph all of those values of X bar for all possible samples of size 100, then I've constructed a sampling distribution of sample means. Remember that each X bar value that we get, each mean of each of those 100 seniors is a mean. Each value is considered a mean. Why are we focused on means? Well, means are less variable, meaning they're going to be more consistent with each other. And it's nice to have things that are more consistent because then they're more reliable than individual observations. If we're looking at only means, then we don't see those extreme values or outliers. We're only focused in on the averages. Yes, some averages might be skewed by an outlier, but when we clump them all together, it's not going to make a huge effect. We won't see GPAs that are very low or very high, only the average GPAs. The larger the sample size, the less variation we're going to see in the values of X bar. So the standard deviation decreases as the sample size increases. That's a very good concept right there, especially for multiple choice type questions. If the sample size is large enough and we have enough of our samples, then our distribution will be approximately normal. Just like it was with proportions. If we had enough of those samples drawn and we plotted them all on the graph, we're going to see a histogram or a dot plot that's approximately normal. Of course, it could never be perfectly normal because we're dealing with data that's discrete. We're just dealing with single values. Normal distributions are supposed to be continuous, so it's very important that you use that word approximately normal. Never say that it is normal. You can say that we're going to apply the normal model, but you can't say that our distribution is exactly normal. Central limit theorem, abbreviated as the CLT, states that if you draw a simple random sample of size n from any population whatsoever with mean mu and standard deviation sigma, when n is large enough, usually when it's at least 30, so at least 30 we're going to write in here, which, yeah, it's not, try again, at least 30. The sampling model, the sample means X bar is close to the normal model. And here's our formula that we're going to get to use right here. So mu is our mean that we're dealing with. And our standard deviation of X bar is going to be the standard deviation that we're given from the population divided by the square root of those sample sizes. Your spread's going to get smaller because you're dealing with averages, and this is how we interpret how small it's going to get. You divide by the size of your sample. If you think about how you calculate an average, you add up all the values and divide by the number of numbers. Well, for the average spread, we're going to take the standard deviation given to us from the whole population and divide by the number of numbers, but we're square rooting that. Why do we square root? Do you remember the variance? That when we multiplied by a constant times the variance, we're really only multiplying by the square root of that constant to the standard deviation. Understanding this formula might be tricky for some of you. Knowing when to use it is the key. If they give you a sample size and they give you the standard deviation, to get the sample standard deviation of sample means, take that standard deviation of your population, this this sigma right here, and divide it by the square root of n, as you want to make it smaller. Assumptions in order to use the normal model. So assumptions to apply the normal model. First one, just like it was for proportions, the values have to be independent of each other, meaning we're told we have a simple random sample. If the problem tells you you have the values were randomly chosen, then you can just repeat that for this assumption and it will be met. If the problem doesn't tell you, then that's where you're going to throw in this condition right here, that the sample sizes, or if we're not told they're independent or a random sample, then your sample size has to be less than 10% of the population, which is also written as the population is 10 times the sample size. And a lot of times this is the part we're just going to have to assume because you're not going to know if it is or it's not. Okay, so that's saying that the sample is small enough, just like we had mentioned before. And I think it was, who was sitting up front? Aaron and Cami, maybe, that Aaron and Isa, maybe it was, that mentioned it was the Goldilocks condition they were going to call it, that this one's saying it needs to be small enough, and this one's saying that it needed to be large enough. The population distribution is normal, then so it's the sampling distribution of X bar. Well, there will be times where they tell you the population is normal. But for what we're doing, probably not. If they tell you the population is normal, then just mention that and you can move on. If the problem doesn't state that the population is normal, mean normally distributed, meaning it pretty much one standard deviation away in either direction is 68% of your data, 2 is 95, and 3 is 99.7. If they don't mention that that is true for your population, then here's your other condition. For proportions, we needed at least 10 successes and 10 failures. For this condition, for means, we're just going to say that your sample size has to be at least 30. Why 30? Well, when we get into it later and we look at our central limit theorem activity, you'll start to see why. That if your sample size is large enough, it's okay that your distribution is going to be approximately normal with that many X bars up there with a sample size of at least 30. So here's our practice. Now, I did make this problem up. It was from me going to the Wild Animal Kingdom in San Diego, and I was shocked at the arm that I saw sitting outside of a cave because the rest of the gorilla was inside the cave, but this arm just was with its knuckles on the ground and the height of the shoulder. It was just extraordinary. So that's where this problem came from. A gorilla expert found that adult male silverbacks have an average height of 12 feet with a standard deviation of 1.25 feet. The scientists collect a random sample of 45 adult male silverbacks and measure their heights. In their sample, the mean height was 14.3 feet high. One of the scientists fears that the gorillas are evolving into larger animals and worries that they may one day grow so tall that they would become a dangerous threat to our way of life. Do you think the sample result is unusually large? Explain. Now, of course, this is a little made up, so yeah, gorillas probably aren't going to take over the world, but let's just play along for right now since I made this problem up. Reread the problem, circle the numbers, and identify what they are. This 12 is our mu. Oof, this board. Okay, take a little time out real quick. Let me recalibrate one more time. Third time has to be a charm. So here we go. 12. Okay, 45. That's going to be your N. That's how many that were chosen. And note, they were randomly chosen. 14.3, that's your X bar. And you also have 12 equals your mu. So, first part says state what we want to know. Go back to the last couple lines, and we want to know if an average, okay, I'm going to try again. So we have that mu is 12, that n is 45, that x bar is 14.3. And one more thing that I left out here is that standard deviation from the population, sigma, is 1.25. So I know Colin Kubista asked today in class, he really wasn't sure where we were going with this. So if that's you, start thinking about where are we going with this? We want to know, is 14.3 unusual? And that's exactly what we're going to write down here. We want to know, is 14.3 feet an unusual, now I can't spell, average height? For an adult male silverback. So in your mind, or you can make a sketch because you know what's coming later, we're starting to wonder, here's our normal curve. We know that 12 is going to go in the middle, and 14.3 is way over here. Is that height or larger extreme? So now we got to check our conditions. Before we can even actually draw that normal curve, the conditions have to be matched. So are they independent? Go back to the problem. Oh yeah, we underlined the word random before I recalibrated. So all we have to write here is the 45 male silverbacks were randomly chosen so that condition's met. Now this second bullet's really my mistake. We don't need to say that the sample size is less than 10% since we know that they were randomly chosen. Instead, what we want to say here is, do we know if the population's normal? That is something we should never assume. And since the problem doesn't state anywhere that the population was normal, then it is based on our sample size. So is n greater than or equal to 30? Well, yeah, we have 45. So I'm going to write 45 is also at least 30. I could put it more in context, but I already did that in the first condition. So down here in part C, those were the two conditions we had to meet. Done. So we say with conditions met, we can apply the normal model with mu equal to 12 and standard deviation for our sample mean. Oh, so messy. and the standard deviation for our sample mean, that's just a little subscript. Again, you can write out the word standard deviation, equal to the 1.25, which was the sigma from the problem, standard deviation of the population, divided by the square root of n. We had 45 male silverbacks. Remember, this is because our spread of the means is supposed to be drastically smaller than the true population values. And again, you will see that illustrated with the penny activity in the central limit theorem. When you compute this, you get, I believe it's 0.186. So make a picture. I did that up above. It was a little messy though, so let me try again. Got 12 in the middle. 14.3 is the part in question. That is a 14. And I'm shading above. Then I need to figure out my z-score calculation. So z is going to equal 14.3, our x, what we're worried about, our sample mean, minus 12 over 0.186. Since I showed the work above, I don't need to show it again. And I end up with a z-score of 12.366. So is that extreme? Well, if you put it in your calculator to find the probability of z being greater than that, remember, 3 standard deviations away in either direction is almost 100% of your data. It's 99.7%. We're talking 12 standard deviations above the mean. You put that in a normal CDF, put 12.366. I don't know, is 5 going to work? 5's not bigger than 12. Your calculator is probably not going to like you for that. So, who knows? Let's try 25. You do 50. You put that in, and you end up with, don't get fooled by the calculator, because some of you might want to say 2% or 200% in this case. But no, it's 2.06, and then there's a little e way over here in your calculator, really meaning times 10 to the negative 35. So when you come up with a result like that, you could just say basically 0. In fact, back here, if you identify 12 as being a very extreme z-score, which it is, you could just stop right there and say that this is basically 0. It's understanding that that many standard deviations away is extreme and very unlikely to happen. So with all that said, I think we need to alert the proper authorities and start searching down and hunting down these silverbacks, because they are just growing at an extreme rate, and eventually if we don't contain them, they will take us over. Kidding. So what we want to write in context. First, it asked way back up. This is the ticky-tack stuff for the AP exam. Do you think the sample result is unusually large? Since they phrased it that way, we have to answer the question. So they want a yes or no answer first. So yes, this sample result of 14.3 feet is unusually large. And has a 0% chance of occurring if the true average height of adult male silverbacks. Is 12 feet. Now, this last part where I wrote the if, you could have stopped it at occurring. You don't have to add in this part yet. That part is thrown in there when we go to our hypothesis test and talk about the probability of getting the result so extreme when we call it the p-value. So again, we are dealing with sample means and doing a sampling distribution of sample means. Quiz next class, depending on when you're listening to this, will be on just section 7.1 and 7.2 because I understand we haven't gone through this in detail yet. So please reread the section and try those book problems, and hopefully we'll be on the right track that we can clear up any questions you have before the quiz. Thank you.